Welcome to part 1 of chapter 12. Today's lecture is all about acids and bases. So our first definition of an acid is the definition of an ARRHENIUS acid. An ARRHENIUS acid is an acidic solution that contains an excess of hydrogen ions. Okay, you would likely recognize acids kind of out in your life as something that tastes sour. Like here, they have a lemon, or maybe it's an orange. It's a bit hard to tell. But either way, they have a citrus fruit, right? And if we eat citrus, we associate that with a sour taste, right? You kind of pucker up your face, and it's sour. The same thing would be true if you were to kind of taste an acid in lab. Again, never taste anything in lab, right? Do not put anything in your mouth. Could be really dangerous. But if you were to, then all of those acids we've been working with, they would taste sour. A way that we would recognize an acid in lab, because obviously we can't go around tasting all of our chemicals, is we use litmus paper. Litmus paper is cool. It's this like little strip of paper, and you can stick it into solutions and it turns colors. So our litmus paper will turn either pink or red in an acidic solution. So that's how we would know that something's acidic rather than tasting it, which again, not super safe. From a reactivity standpoint, we recognize that something is an acid if it reacts with a metal to produce hydrogen gas. It's kind of a cool reaction. You can put like a piece of metal, maybe zinc or aluminum, and put it in some acid and it will start to bubble. We actually see this in a lab that we do in this class, right? So we see these bubbles, and those bubbles are hydrogen gas, and you can actually light those bubbles on fire because hydrogen gas is flammable, so kind of cool. But we would see that bubbling, so that would let us know that something's acidic because it's reacting with the metal. We have learned already that an acid reacts with a base to give a salt and water, right? So if we see say we knew something was a base and we added this mystery thing to it and it reacted, we would know that that's an acid because acids and bases will react to form a salt and water. They will give a neutral solution, which we'll learn about a little later in this lecture. And then if they were to react with a carbonate like marble, right? Marble is calcium carbonate or chalk. These acids would react and produce carbon dioxide. So again, we would see bubbles, right? One of them would be flammable gas, which is hydrogen, and the other one would not be. But a lot of times when things are reacting with acids, we see bubbles, which is kind of cool. So these are some properties of acids. And again, we are saying that an acid contains an excess of H+ ions. Okay, so again, ARRHENIUS says they will produce H+ ions in an aqueous solution. So for a compound to do this, it has to have a hydrogen atom in the first place. Okay, but it has to specifically have a hydrogen atom that can separate from the molecules when we are dissolved in water. So these are what's called ionizable hydrogen atoms. So kind of like when we were talking about net ionic equations and things dissociating in water, we need to have a compound that has a hydrogen that can kind of come off when it's in water. Not all hydrogens can do that. We don't get much into that in this course, so we're just going to kind of look at a couple specific examples, but more on that in later chemistry classes if you're interested. So a lot of acids will have just one ionizable hydrogen. Sometimes they have more than one. Mostly they'll just have one though. But if they have more than one, it's going to look like this. So here's H2SO4 or H3PO4. Again, we recognize acids because they will have an H in the front. That's how we are going to recognize an ionizable hydrogen. So these are hydrogens that can come off when we put them in water. For like example, hydrochloric acid will separate into hydrogen and chlorine. So that hydrogen came off when we put it in water, right? It dissociated because this is an ionizable hydrogen. So for these two, like sulfuric acid, this has 2 ionizable hydrogens. So it would produce 2 H+ in the water. And this has 3 ionizable hydrogens, so it would produce 3 H+ in the water, right? But again, in this class, we are going to recognize ionizable hydrogens as the ones in the front. Those are the ones that can come off when our acids are dissolved in water. And we'll recognize acids because they will always have an H in the front. If the H is anywhere else in the molecule, this is not an ionizable hydrogen. It will not come off when we put it in water. Therefore, it's not an acid. Okay, so the H pluses that come off of these things, all right, these hydrogen ions, they are super reactive. Okay, really, really, really reactive, and they actually cannot exist by themselves in water. They are just protons, right? So if we think about a hydrogen, right, if you looked at the periodic table, you find our hydrogen. Hydrogen has H, its atomic number 1, it has a mass of 1.008. Okay, so just kind of a quick review, this number up at the top tells us that hydrogen has 1 proton, okay? And since it has 1 proton and our atoms are neutral, it also has 1 electron, okay? This mass at the bottom tells us the total number of protons and neutrons. So we know it already has 1 proton, but since this mass is 1, that actually means it has 0 neutrons, which is kind of interesting. Hydrogen is the only atom that can exist with no neutrons. So this is just kind of a quick review from earlier in the semester, but what I'm trying to get at here is that hydrogen just has a proton and an electron. So if it forms H+, that means it lost an electron. So really, H+ is just a proton, right? If it loses this electron, all it's got left is a proton, which is kind of weird. So when we talk about H+, we'll often, in higher levels of chemistry, call them protons because that's what they are. So kind of weird to think about. Anyways, long story short, protons floating around by themselves are super reactive. So essentially what that proton does is it just kind of grabs on to the nearest molecule. And since all of these reactions are being done in water, the nearest molecule is usually a water molecule. So instead of it floating around as H+, it grabs onto a water molecule and forms H3O+. This is called the hydronium ion. So when we're talking about acids, a lot of times we will talk about H+ and H3O+ as if they are the same thing. And in reality, they are. The only difference is here, one has grabbed onto a water molecule and the other one hasn't. But like I said, they won't exist like this in solution. It will always be this. So even if we're talking about H+, I want you to think, okay, that's the same thing as H3O+. We use those terms, H+ and H3O+, interchangeably in chemistry because both of them mean the presence of an acid, because this won't be there unless this was there. Okay, so H+ and H3O+ mean the same thing in chemistry. And again, the reason for this is that proton just grabs onto water and forms H3O+. Okay, so here's some common acids you may be familiar with just kind of in lab or in your life. We work a lot with hydrochloric acid in chemistry. Hydrochloric acid is actually also the component of your stomach, right? When we talk about stomach acid, that is hydrochloric acid. So kind of weird to think about, in my opinion, right? That stuff that we usually use in a bottle, that is the same stuff that is existing in our stomach that's used to digest food. Another one that we kind of work with in lab is sulfuric acid. We also use nitric acid. Nitric acid is kind of interesting. It's used in fertilizer and it's used in explosives. Acetic acid is just vinegar. Okay, vinegar is essentially diluted acetic acid. Citric acid is like in lemons and limes. It's also in your sodas a little bit. Carbonic acid is also in your sodas. It produces carbon dioxide. Yeah, lots of acids. We use acids a lot in our daily lives. So if you've been kind of thinking to yourself, like, why do I need to know chemistry? This is one of the reasons, right? We run into acids all the time. Okay, so if we are talking about acids, we also need to talk about bases. So our Arrhenius definition for a base is a solution that contains an excess of hydroxide ions. Okay. So if you were to, again, taste a base, right? Don't taste anything in lab, but if you were to taste something in lab, it would taste kind of bitter. The way that I always think about this, I don't know if when you were a kid, your parents ever had to wash your mouth out with soap, or if you've ever, gotten soap on your hands and actually accidentally put them in your mouth. It kind of has like a bitter taste, right? That soapy bitter taste, that is what a base tastes like. It's in high levels, it's also caustic, which means it will burn you, okay? But low levels of base just kind of taste bitter. It will turn litmus paper blue. Remember that litmus paper I was talking about earlier, that little strip of paper? Litmus paper will turn pink or red in acidic solutions, but it will turn blue in basic solutions. So litmus paper is really cool for figuring out the acidity of our compounds. Okay. If you were to touch a base, it would taste, or it would feel kind of slippery. Okay, that's a really good way to notice in lab. If you have a base on your hands, it'll feel kind of slippery, and that should be your cue to go immediately wash your hands, because otherwise that base is going to burn you really, really quick. Okay, and the reason that we typically use bases is they're really helpful in neutralizing acids. For example, you may have taken like if you have an upset stomach, right, that's an excess of stomach acid, right? Maybe you've got heartburn, indigestion, right? But usually it's because of an excess of acid in your stomach. So we would go then and maybe take some Tums, right? Because they are an antacid. Well, really, when we talk about antacids, those are actually bases. We just call them antacids to market to the general public, because if we told people there was going to be an acid-base neutralization reaction happening in your stomach, people were like, whoa, I don't want to take any chemicals, right? That's kind of a common thing that people say. But so we market them as antacid rather than a base. But essentially you take some Tums because they're a base and they will neutralize the acids that are present in your stomach. Kind of cool. So this is ammonia. This is a type of cleaner that people will use on occasion. As you can see, this litmus paper has turned blue. So like I mentioned earlier, our definition for a base is that they produce hydroxide ions in aqueous solution. So in order to do this, they need to have a hydroxide ion in their chemical formula. So here is sodium hydroxide. So again, we are recognizing a base because they have an OH at the back. So when we put this sodium hydroxide into water, that will break into sodium and our hydroxide ion. So this is how we recognize it's a base. It will have hydroxides floating around. So this is in contrast to our acids, right? Acids had an H in the front, and our bases will have a hydroxide in the back. Those are how we'll recognize those two different species. So we don't run into bases as frequently as we talk about acids, but in lab, we typically will use sodium hydroxide. That's a really common base. It's pretty cheap. Out in the world, we use it in soap and plastic manufacturing, and it's used a little bit also in petroleum processing. You may also have heard of potassium hydroxide. It's used in cotton processing, especially like in electroplating. We see it in some batteries, right? But essentially what I want you to notice here is that both of these have a hydroxide ion in the back here. So we will recognize them as bases. There are other bases that we will run into in higher levels of chemistry that don't have these hydroxide ions in the back, but we are not going to worry about those in this class. For this class, I only want you to notice it's a base if it has a hydroxide ion. Okay, so our ARRHENIUS acid-base reactions. Essentially, the way this plays out is the H plus from the acid combines with the OH from the base, and it makes H2O, right? We would have 2 hydrogens and an oxygen, so that's H2O. And then whatever is left over, so that cation from the base and the anion from the acid combine to make a salt. And remember, in chemistry, when we talk about salts, these are just another term for ionic compounds, okay? It's not often table salt. Every once in a while, like this specific example, this is table salt. But the word salt just means ionic compound. It just means it's not an acid and it's not a base. Therefore, it's a salt, okay? So if you see that term salt, it doesn't mean necessarily sodium chloride. It can, but it doesn't necessarily mean that. So in this example here, we have our H plus combining with our OH. So those two pieces, that H plus and the OH, those are what's going to make water. Okay, so everything else this chloride and this sodium, that's going to make our salt. Okay, and again, in order to make our salt, you would need to circle and switch the ions just like we've done before. So this would be Na plus and Cl minus, and that will get us NaCl because those charges are equal and opposite, so we just put them together, right? All of our rules of writing formulas for ionic compounds and all of that, that still applies here. This is just a specific type of reaction. So our general formula is an acid plus base will give us a salt and water. Alrighty, I want you to go ahead and pause here and complete problems number 1 through 7 on the Chapter 12 lecture worksheet. Once you're done, come back and we'll keep going. Alrighty, so we've already learned the Arrhenius definitions for an acid and a base, and those are pretty good definitions, especially for the level of this class. There is another definition, though, called the Bronsted-Lowry definition that is kind of more general and allows us to classify more things as acids and bases. Okay, so instead of saying, okay, acids make H plus in solution and bases make hydroxide in solution, these are now looking at donating and accepting protons. Remember, protons in chemistry are H plus. So we're just looking at where is the H plus going. A substance that's going to lose our H plus will be an acid, and a substance that will gain an H plus will be a base. So this is just kind of a more widely applicable definition of acids and bases. Again, for the most part in this class, our Arrhenius definition is mostly going to be good enough, but we are going to work a little bit with this Bronsted-Lowry acid-base theory. Okay, so again, we're going to look at proton transfer, H plus transfer from one molecule to another. So if you're seeing an H plus leave one substance and go to the other one, then that is going to be an acid-base reaction. So we're not looking at, are there H pluses in solution? Are there OH minuses in solution? We're just looking at, where did the H plus go? Did a hydrogen ion move from one thing to another? And if so, that's an acid-base reaction. Okay, it's really cool that anything that we were looking at earlier, anything that was an Arrhenius acid base is also going to be a Bronsted-Lowry acid base as well. So like our Arrhenius definition is kind of a narrow definition, whereas Bronsted-Lowry is more broad. So anything that was an acid base before is still going to be an acid base reaction now. We're just going to include more stuff too. Okay, so let's look at this. Anything that is going to lose a proton, if it's going to donate a proton, donate an H plus, then it's going to be an acid. So if it loses H plus, it's an acid. A Bronsted-Lowry base, that's really the definition that's kind of changing. Okay, now we're going to say a base is a proton acceptor. Anything that gains that H plus is going to be a base. So here we have our HCl, so hydrochloric acid, is going to be our acid, just like it was before, right? It has an H in the front, super easy to recognize that as an acid. So what it's going to do here is it's going to lose that H plus, just like it did before. However, you'll notice that our base is not a base like we were looking at earlier, right? Remember earlier with our Arrhenius definition, we were looking at bases as containing hydroxides, and this one doesn't, right? So with our Arrhenius definition, this would not be an acid-base reaction, except under Bronsted-Lowry, it is. Okay, so Bronsted-Lowry definitions are more broad. They're helping us to better understand acid-base reactions. So the reason that this water acts like a base is because this hydrogen is going to leave the acid and join up with the water. So here, our hydrochloric acid is a proton donor because it's going to lose a hydrogen. Our water is going to gain it. Our water makes H3O plus. So that means that hydrogen joined up with water to make the hydronium ion. So water accepted a proton. Therefore, our water here is acting as a base. Okay, so water gained the hydrogen. It's a proton acceptor. Therefore, it's a base. Our acid lost a hydrogen just like it did before. therefore it's an acid. When you have an acid, that means whatever it's reacting with, it's going to act like a base. So here, since water's present, the water is going to act like a base. Water is super cool. Water is what's called amphoteric. And we're not going to get into that a ton. There's a bit about it in your book. But water can act as either an acid or a base. If water is with an acid, then it'll act like a base. If water is with a base, then it'll act like an acid. It's pretty cool. Water has a lot of really cool properties. We're not going to get into that a ton in this class, but you will see it a bit in this Bronsted-Lowry acid and base definitions. Okay, so again, for Arrhenius definition, we said, okay, acids are going to produce H+. And then we said that H+ is going to join up with a water and it'll form hydronium ion. And we said bases produce hydroxide ion in solution. So instead of looking at what ions are floating around in solution, our Bronsted-Lowry definition says, okay, acids will donate a hydrogen, whereas bases will accept them. Okay, so again, our Bronsted-Lowry definition is a more general definition, helping us to better understand acid-base reactions. So since we've been talking about things gaining and losing hydrogens, this leads us to talk about conjugate acid-base pairs. And these are two species that differ from each other by the presence of just one hydrogen ion. Okay, so here's an example. So we know hydrochloric acid is an acid. It has an H in the front. Well, during this reaction that we were just talking about, our water is going to act like a base and our hydrochloric acid will act like an acid. So what happens is this acid will lose a hydrogen, okay? So when it loses a hydrogen, it turns into Cl-, okay? So if this was the acid, this is what's called the conjugate base. So when our acid loses its hydrogen, when it donates its hydrogen, it becomes a conjugate base, okay? So again, this species here, our hydrochloric acid versus our chloride, these are only different from the presence of one hydrogen, okay? That's how we will know this is a conjugate acid-base pair. So this is our acid, therefore this is our conjugate base. Okay, we can do the same thing with a base. So here is a base, and we're not going to talk much about these types of bases, but this is ammonia. It's a very common base. And the way that we know that this is a base is because during the process of this reaction, it gains a hydrogen. So do you see that we have a 3 here? And this becomes a 4 and a plus, right? That means it gained H+ along the way. It gained another hydrogen, and therefore it now has a positive charge. So if this is our base, then this is our conjugate acid, because they are differing by just one hydrogen, okay? So when we see that proton being accepted, therefore our base turns into a conjugate acid. So acids will turn into conjugate bases, bases will turn into conjugate acids. So let's look at this. So here we have ammonia, which I told you was acting like a base in that previous problem. So the reason we know it's acting like a base is because during the reaction, it gained a hydrogen. So we increased the number of hydrogens here and it got a positive charge, okay? So we know that our base turned into our conjugate acid because it gained a hydrogen. So since ammonia is acting like a base, that means our water is going to act like an acid, which means our water will donate a hydrogen. So as you can see here, our water lost a hydrogen, okay? It had 2 hydrogens, now it's only got 1. And when it lost that H+, it ended up with a negative charge, giving us our conjugate base. So our acids will turn into conjugate bases. So let's give this a go. So this says, for a given acid, determine the formula of the conjugate base. So for all of these acids, what they are going to do is they are going to lose a hydrogen. Remember, acids are proton donors. So that means all of these acids will lose a hydrogen, and when they lose a hydrogen, that H+, they will end up now with a negative charge. They lost a positive charge, so they will have a leftover negative charge. So for the bases down at the bottom, remember, they are doing the opposite. They are going to gain a hydrogen. So when they gain that H+, and they were negative before, now they are going to become neutral. Okay, so go ahead, pause here, give this a go, and then come back when you're ready to see the answers. Alrighty, let's go over this. So for each of these acids, remember, acids are proton donors. So essentially what this means is they will lose an H+. So when they lose an H+, they're losing a positive charge. They're going to lose a hydrogen and they're losing a positive charge, which means they will end up with an overall negative charge. So it's going to look like this. So our HF loses the hydrogen and then becomes negatively charged. Okay, our next one, we are going to lose a hydrogen and again become negatively charged. So it'll look like this. You'll notice though, it still has one hydrogen left over. Okay, it still has one hydrogen left over because for a conjugate acid-base pair, you can only differ by one H+. Okay, so it can only lose one hydrogen here, which means it'll still have one, and then it gains the negative charge. Our carbonic acid will do essentially the same thing. It will lose one hydrogen, but still have one hydrogen left over, and again, will have a negative charge. So these are acid-base pairs. All of these are acids, and all of these are conjugate bases. Okay, so again, they're just what happens to the acid after it loses that H+. For our bases, remember, they are going to be proton acceptors. Okay, so essentially they are going to gain H+. So when they gain H+, they're going to gain a hydrogen and they are going to lose that negative charge because our positive and our negative will essentially cancel out. So for our first one, it already has two hydrogens. So when it gains one, now it's going to have three and it's going to lose the negative charge. Sometimes I'll see people write this. So check and see, did you write that? So if you did write that, don't do that anymore. Essentially what happens is that hydrogen that was gained is an ionizable hydrogen like we were talking about earlier. So it needs to go in the front and join up with all of those other ionizable hydrogens. So any hydrogens that can be lost or gained in acid-base reactions always will go in the front. Okay, hydrogen at the back mean a different thing that we're not going to get into in this class. All right, let's look at the next one. So that's sulfite. When it gains a hydrogen, remember, it's just going to gain one hydrogen because these are acid-base pairs. So when it gains one hydrogen, that hydrogen goes in the front and it's left over with a negative charge. It had a 2- and it gained a positive, leaving us with a residual 1- charge. Okay, and then our nitrate down at the bottom will gain one hydrogen, and that hydrogen, that positive charge, will cancel out the negative charge, and we'll just get that. Okay, so again, all of these are differing by one hydrogen. Acids will lose H+, and they'll usually end up with a negative charge like we're seeing because it's lost that positive. Whereas our bases will gain a hydrogen and become more positive. Alrighty, let's try this. This says label each of the species in the following equations as an acid, a base, a conjugate base, or a conjugate acid. Okay, so on the left-hand side over here, right, the left-hand side, our reactants, that's where we're going to have either acid or base. So those are kind of your options. You got to pick one. It's either going to be an acid or a base. For the stuff on the product side, that's where we're going to label it as a conjugate base or a conjugate acid. Remember, acids turn into conjugate bases, and bases turn into conjugate acids. Okay, so go ahead, pause here, try this out, and then come back when you're ready to see the answer. Alrighty, so going over this, you see the H in the front of HF, that's telling you that this is an acid, just like normal, okay? So if that's an acid, that means this one has to be a base. Okay, so I think that's pretty straightforward. Remember, we're going to label the stuff on the left as either an acid or a base. So if you know which one's the acid, then the other one is the base. Okay, so now our acid is going to turn into the conjugate base. So if we know this is the acid That's its matching pair essentially on the other side. That is the conjugate base. Remember, they're always going to differ by the presence of just one H plus here. So here our acid has lost its hydrogen and become a conjugate base. Our base will always become a conjugate acid. So here our base gained a hydrogen and became the conjugate acid. Okay. All right, let's look at the next one. The next one's a little bit trickier. So we see water, and we know water can act as either an acid or a base. So we need to figure out what is the other thing. Well, the other one is acetate. This trips people up a lot because they're like, okay, there's no hydrogen in the front, there's no OH in the back, so what is that, right? If you look, throughout the course of this reaction, this turned into HC2H3O2. So what happened, what's the difference here, is that it gained a hydrogen during this reaction. So since it gained a hydrogen, that means it was a proton acceptor. Okay, so since it's a proton acceptor, this is a base. So again, this doesn't meet our definitions of the Arrhenius acid or bases, right? It doesn't have an H plus, doesn't have an OH minus, but this is an acid-base reaction because we're seeing a proton transfer. Okay, so we have to use our Bronsted-Lowry definition. Since this species, right, this acetate ion, gained a hydrogen along the way, that means it's a proton acceptor and it's a base. So therefore, water is going to act like an acid. So that's how we get the base and acid on the left-hand side. If this was a base, when it gains a hydrogen, that means it's going to be the conjugate acid. And since water was acting like an acid, it becomes the conjugate base. Alrighty, let's go ahead and get some practice on this. Go ahead and complete problems number 8 through 15 on the Chapter 12 lecture worksheet. Once you're done, come back and we'll keep going. So before, we were talking about determining whether our solution was acidic or basic using litmus paper, right? We said we can use that litmus paper. If it turns pink or red, then that means it's acidic. If it turns blue, that means it's basic. But it's not that precise, right? It doesn't tell us, well, how acidic or how basic, right? It's not just black and white. We need to know in chemistry the concentration of our hydronium ion, right? How acidic it is, how basic it is, because chemistry is a math-based course. So we need to be able to associate some numbers to tell us how acidic something is or how basic something is. So essentially what we're looking at is our concentration of hydronium ions. Right, remember, we're getting hydronium ions because of the H plus floating around from the acid. That H plus will grab onto a water molecule and give us H3O plus. So the more H plus that's in there, right, the more acid we have, then the more H3O plus we have, which will increase that molarity. So we could just use the concentration of H3O plus to tell us how acidic something is, right? More H3O plus, more acidic. Less H3O plus, less acidic, right? And we could do that, but this concentration has a huge range. Big orders of magnitude, we have to use scientific notation, and it's a bit cumbersome to work with. Okay, so instead, we will describe the acidity of our solution using the pH scale. And the way the pH scale works is we're just going to take the negative log of our concentration of our H3O plus ion. So when you type this in your calculator, you would just put negative, you'd hit that log button, and then type in the molarity of your H3O plus concentration. And now that will make your pH a whole number, which is much easier to work with and to talk about. Alrighty, so our definition of pH is the negative log of the concentration of our hydronium ion. And this concentration is going to be in molarity, which we've learned to calculate earlier. So if we looked at pure water, pure deionized water, our hydronium ion concentration is 1 × 10⁻⁷ molar. So if we take the negative log of that number, we would get a pH of 7. So that would just be for normal deionized water like we use in lab. So we say, okay, if something has a pH of 7, that makes it neutral because it's essentially just water. anything that has a pH that's less than 7 is going to have a really high hydronium ion concentration. And if it has a really high hydronium ion concentration, that means it's acidic. You'll notice that the color of the pH scale on that side is pink, which we associate with an acid when we use litmus paper. So it's kind of tying it all together. The side that has the pH greater than 7, that means it's going to have a very, very small hydronium ion concentration. And that's going to give us a base. So everything on the right-hand side here with a pH greater than 7 is going to be basic, which is why it's showing up as blue to kind of correspond to that litmus paper. Okay, so essentially, if we want to figure out whether something is an acid or a base, we can measure the hydronium ion concentration and then take the negative log, and we can calculate our pH and compare it to this pH scale. Again, 7 is neutral. Anything that's less than 7 is acidic, and anything that's greater than a 7 is basic. Okay, so let's look at some real-world examples. So the first one is gastric juice. That means the stuff in your stomach, so our stomach acid. That has a pH of 1.0. I know that doesn't sound very impressive, but that means it's really, really acidic. That means it's the same as 0.1 molar hydrochloric acid, which we work with in lab. And I tell you, make sure to use all this caution, rinse your hands, all of that stuff. That's why I know this is going to sound gross, but when you throw up and it, feels like it's burning the inside of your throat, it's because it is. Right? Essentially what you're doing when you throw up, you're coating your throat, the inside of your throat, in acid. And so if it feels like it's burning, it is. And the solution to that would be to drink a lot of water and try and, get that down. Obviously, if you have an upset stomach, don't just chug a bunch of water or that can make the problem worse. You can see other things that we associate with acidity is like lemon juice and vinegar, right? Both of those are acids, and you'll see they have very low pHs as well. Orange juice is also acidic, so is coffee. And so all of these things, right, and you've probably heard this, you don't want to drink too much of anything that's acidic because that can upset your stomach and alter the pH of the stomach contents, which is why sometimes you'll feel like you get heartburn or, your stomach feels acidic because maybe you've drank too many things that are acidic. And so you may want to take Tums or something else that's, quote unquote, an antacid or a base to kind of start to neutralize that acidity. You'll see our pure water here is at 7.0. So anything that's this way, this is all acidic, right? Because it has a lower pH than 7. Anything that's down here, that would be basic. Your blood is actually very slightly basic, which is kind of interesting. It's a buffer solution, which you'll learn about more if you go on to higher levels of chemistry. But for the purpose of this class, it is slightly basic. Mostly neutral, right, because it's got pretty close to 7, but it is slightly basic. Ammonia, like we were talking about earlier, is basic, and 1 molar sodium hydroxide, which is a common base that we use in class. All right, so our pH number is telling us how acidic or basic our solution is. Again, if we have a very, very low pH, right, so something that's like 0, that's going to tell us it's very, very, very acidic, okay? Our typical pH is 0 to 14. So 0 would be like the most acidic, and then 14 would be really basic. Spoiler alert, it can actually be outside of this range. It can actually be a little bit negative or a little bit higher than 14, but pretty typically it's somewhere between 0 and 14, okay? So the lower it is, the more acidic it is, and the higher it is, the more basic it is, with, again, our 7 being absolutely neutral. So let's try this out. This says determine the pH of a solution at 25 degrees Celsius in which the hydronium ion concentration is 3.5 times 10 to the minus 4th molar. Okay, and then I want to know, is it acidic, basic, or neutral? Okay, so for this, we're not going to care that it's at 25 degrees Celsius. The reason that's included here is because the pH will change slightly when we're at different temperatures. But that's not going to matter for this class, so you can go ahead and just ignore that bit. Okay, so essentially what we need here is the hydronium ion concentration is 3.5 times 10 to the minus 4th molar. To figure out the pH, we are going to take the negative log of that number. Okay, so when you plug this in your calculator, you're just going to put negative log, and hopefully you know where that log button is on your calculator. If you don't know, go ahead and send me a message and I will, you can even send a picture of your calculator and I'll show you where that log button is. But you'll just type negative log and the concentration in molarity, okay? And then that will give you a number. For this class, I don't want you to worry about significant figures as they apply to pH. There are rules that go with this if you'd like to look them up, but for this class, I will not be grading significant figures as it relates to pH. I would just give me 2 decimal points, kind of always. So here, if we take the negative log, we get 3.46. So since this pH is less than 7, this is acidic. Okay, so again, try not to make this any harder than it is. If you've got your concentration, you'll just type in the negative log of that concentration, you'll get a number, and then you'll compare it to 7. If it's less than 7, it's acidic. If it's greater than 7, it's basic. All right, I want you to try one now. This says determine the pH of a solution in which the hydronium ion concentration is 8.8 times 10 to the minus 11th molar. Okay, so figure out the pH and then tell me whether it's acidic, basic, or neutral. Go ahead and pause here and then come back when you're ready to see the answer. Alrighty, so if we take the negative log of that number, then we get 10.06. Since that number is greater than 7, that means that this solution is basic. Alrighty, let's try it a little bit differently. This says calculate the hydronium ion concentration in a solution in which the pH is 11.95. Okay, so now this is asking us to go backwards. Okay, now it says we have the pH. What is the hydronium ion concentration? Okay, so this is not as straightforward as kind of addition subtraction. So here's our equation here. So this says pH is equal to the negative log of the hydronium ion concentration. You may remember from math, the way to get rid of this negative log is to do the 10 to the minus. If you don't remember that, then you can just remember a separate equation. Okay, our hydronium ion concentration will equal 10 to the minus pH. Okay, very important that you remember to put the negative here. So to figure out our hydronium ion concentration, we're just going to do 10 to the minus 11.95. Okay, so 10 to the minus pH, and that will get you our hydronium ion concentration. And remember, our unit for this is molarity. Okay, I don't want you to worry again about significant figures here. You can just give me 1 digit past the decimal or 2, whatever you like, but do not worry about significant figures as it relates to anything to do with pH. Alrighty, let's go ahead and get some practice. Complete problems number 16 to 21 on the Chapter 12 lecture worksheet. And that is actually the end of this lecture. We learned a lot about identifying whether something was an acid or a base using 2 different definitions, right? One was our Arrhenius definition, and the other was our Bronsted-Lowry definition. Okay, one of them, right, our Arrhenius definition, looked at the ions that are produced in solution. Acids make H+, and bases make OH-, whereas our Bronsted-Lowry definition was looking at our proton transfer. Our acids are proton donors, whereas our bases are proton acceptors. We use that then to talk about conjugate acid-base pairs and recognizing whether something was losing or gaining a proton. We wrapped everything up by talking about pH and how that pH number can tell us whether something is acidic or basic. Anything less than 7 will be acidic, and anything greater than 7 will be basic. Okay, so make sure you get a lot of practice doing this. And as always, if you have any questions, please let me know. I'm more than happy to chat with you about it and kind of clear up anything that's causing you issues. Otherwise, make sure to work hard on that Chapter 12 lecture worksheet, and I will talk to you guys next time.